Okay, welcome to my talk from the discrepancy of stratified samples to greedy energy minimization. I'm talking here from my home office, and I would like to thank the organizers for giving me the opportunity to present my research result in this talk. So this presentation is split into 3 parts. In the first part, I will just give the basics of uniform distribution theory, which is tailored to the results of my research. So everybody who is already familiar with uniform distribution theory is very welcome to just skip the first part. In part 2, I will present the results that appeared in a recent preprint together with my colleague from Aarhus, Markus Kiedelen. So it will be about discrepancy of stratified samples. We will work with partitions of the unit cube and study how such partitions can give you point sets that are very well distributed. And in the third part, I would like to present results of a recent paper, which was called Greedy Energy Minimization and the Van der Korput Sequence. So both papers can be found on arXiv. And yes, this brings me to the introduction and to the first part. So the main questions in uniform distribution theory are always how to distribute n-points in a uniform manner. Imagine you have a finite number of points and you would like to distribute them in a line segment, in a square, on a sphere. How can you do that? What are good constructions? How can you achieve a good spatial spread of the points, and how can you actually quantify this distribution? Related to this, you can also wonder, well, how to distribute an unknown number of points so that the distribution is uniform. And you can imagine this is a much harder problem, or in a way it's a more difficult problem. You can see here in the middle picture, we distributed a certain number of points, and now the question is, well, where should I place the next point, which is the red dot in the right picture, so that the overall distribution remains good? And to illustrate this problem further, you can imagine you have a square number of points to distribute. Well, you may want to distribute them on a regular grid, but then here you have the problem where to distribute the n plus first point. Wherever you distribute it, you will create local irregularities. And the main question of uniform distribution theory is how to construct robust point sets so that you can always add another point without destroying the overall structure. So to make the concepts more formal, well, we can define a counting function. So we are working in the one-dimensional unit interval for the moment. Let capital J denote a subset of the unit interval, and capital A counts the number of an infinite sequence omega, the number of the first elements of this sequence omega that lie in the interval J. So it's the number of indices for which xi is in J. And then we say that an infinite sequence omega is uniformly distributed modulo 1 if for every subinterval this limit relation holds. So in the limit, every subinterval J should get a fraction of all points that correspond to its measure. So lambda will always denote the Lebesgue measure. So this would be in the one-dimensional setting, it would be the length of the interval. So asymptotically, every subinterval should get an amount or a fraction of points that corresponds to its length. And a next question is, well, how to quantify this property? And for this, the discrepancy was introduced. So you can define the so-called discrepancy function. So the discrepancy function is just the difference between the fraction of points in your interval and the length of the interval. And you take here the absolute value because you can either have more points or less points than what would correspond to the precise value of the length. And discrepancy is now defined as the supremum over all subintervals of 0, 1, and as the supremum of the values of this discrepancy function for all subintervals. You can also restrict the class of intervals. So here we consider arbitrary intervals. If you restrict to intervals anchored at 0, then we speak about the star discrepancy. As a little illustration, you can see here a two-dimensional setting. So we distributed a certain number of points in the two-dimensional unit square, and these red boxes denote two-dimensional axis-aligned boxes or intervals. So you can define discrepancy, of course, also in the two or d-dimensional setting. And here, for example, we can look at the left box. This box has a certain volume. In our case, it's a 12 times 12 box, or and then you can count the number of points. So this box contains 5 points. In total, we have 31 points. So the number of points is 5. The size is 12 times 12. So we normalize by 31, and we get the discrepancy value of 11/31 for this box. And we can repeat this game for all axis-aligned boxes. We can calculate the discrepancy value for all of them, and the worst box we can find is the value of the discrepancy function. And you can already see, if you compare left and right, that there might be differences. So for example, the same box for a different point set can have a much larger discrepancy value because there are many more points inside, and this is just a too big fraction of points compared to the volume of this box. The important theorem in this context is that a uniformly distributed sequence can be characterized via its discrepancy. So there is this classical theorem that the sequence is uniformly distributed modulo 1 if and only if the discrepancy goes to 0 when the number of points go to infinity. And related to that, there is another characterization of uniform distribution, which basically says that the sequence is uniformly distributed modulo 1 if and only if for every real valued continuous function defined on the unit interval, we have this equality here. So we can approximate the integral of this continuous function by a sum of pointwise evaluation of the function. So this is the mean value of the evaluation of the function at the first n points of your sequence. And if this sum converges as n goes to infinity, you should get the value of the integral. And this property is used to define uniform distribution in abstract spaces. So this property of being able to approximate the integral of continuous function can be studied also in more abstract spaces. Before I come to my own results, there are some further interesting and important bounds on the discrepancy that I would like to present to you. So as a side remark, you can imagine if you have a finite number of points in the unit interval, then the most uniform way you can distribute a fixed finite number of points is always to just space them in an equidistant manner. However, the game is a little different if you go to an infinite sequence and you just ask about the discrepancy of the first n points of this infinite sequence. So if you have finitely many equidistributed points, the discrepancy will always be about 1/n. However, if you have an infinite number of points, so you will always gain a log n factor, which basically comes back to the pictures I have shown you before. You always have to make a compromise to ensure that if you add the n plus first point, the overall distribution is still good. So at every point you make a little compromise, and this is basically this additional log n factor that comes in. So this classical result was shown by Schmidt, and it basically says that there exists a constant, a positive constant c, such that for every infinite sequence, the discrepancy can be lower bounded by a constant times log n over n for infinitely many n. So there will always be a situation in which the discrepancy is strictly worse than 1 over n. And this lower bound turns out to be best possible in the one-dimensional case, and this leads to the term of a low discrepancy sequence. So if you have an infinite sequence of points such that its discrepancy can be upper bounded by log n over n, then you say this is a low discrepancy sequence. And this asymptotic constant that you get via this limit superior relation can be used to compare different infinite sequences. So assume you have two low discrepancy sequences and you wonder, well, which one is actually better or is better distributed. Then you can calculate this asymptotic discrepancy constant for both of them, and if this value is smaller for one sequence than for the other, then you can conclude, well, in a certain way, this sequence has a better asymptotic distribution than the other one. And this result was originally shown for the d-dimensional case, so Schmidt just gave an improvement for the one-dimensional case, but originally the result goes back to Roth, who showed that the discrepancy of a d-dimensional sequence can always be lower bounded by log n to the power d over 2 divided by n. So this turns out to be sharp for the L2 discrepancy. I will talk about this notion of discrepancy in the second part. And it is still an open question whether this is also the right order of magnitude for the star discrepancy or the extreme discrepancy. There are sequences whose order of magnitude is log n to the d over n, and so it became customary to call such sequences low discrepancy sequences in higher dimension. This is related to the fact that some people believe this is the right order, while others argue the order might be different. So what you can see here are just three different plots of two-dimensional point sets. So on the left-hand side, there is a regular grid, and it can be shown that the discrepancy of the regular grid is always of 1 over n to the d to the 1 over d. Whereas in the middle, this is a set of random points, and it can be shown that discrepancy is always 1 over n to the 1/2. And on the right-hand side, you have a low discrepancy sequence with a discrepancy of order log n, the d over n. So what I would like to emphasize here is that the random points that you can find here are usually used in Monte Carlo integration, and they are attractive because their discrepancy bound is independent of the dimension. So this bound holds for all dimensions, whereas the regular grid gets worse as the dimension increases. And if you think back of the definition of the discrepancy, this somehow makes sense because you have very large empty boxes between rows of points in the two-dimensional case, and this of course generalizes to d-dimensional boxes. Whereas you can see in the case of a low discrepancy sequence, you can never find as large empty boxes as you can find in the case of the regular grid. And just as a final remark here, so in the case of random points, you can always observe this clustering. So this is due to the fact that these points are all independent random variables, so they do not know anything about each other. And it turns out that this leads to a certain kind of clustering, which you circumvent by clever constructions in the case of low discrepancy point sets. And this phenomenon will be important also in part 2. So to sum up this first part, there are several known constructions of low discrepancy sequences. Most of them are based on structures or methods from number theory or from combinatorics. So on the one hand, we have van der Corput and Holton type sequences, also more general digital sequences, which are usually based on p-adic expansions of numbers. And on the other hand, we have N-alpha type sequences, which are usually based on Diophantine approximation and on properties of irrational numbers alpha. So these are two distinct construction principles, which are well established and studied. However, especially with respect to this conjecture that I mentioned about the right order of discrepancy, it would also be very interesting to have other ways of constructing low discrepancy point sets. And the aim of the following two parts of my talk is to study different alternative ways of constructing very well distributed point sets and sequences. Okay, so that's the end of part 1.